The first thing you want to tell yourself when you hit a problem like this is don't freak out, right? They're giving you an equation. A lot of times people freak out when they start seeing that x up in there in an integral like this, but that's just the equation and you're not really sure what they're going to ask you to do with it yet. So, don't get too freaked out too quickly on something like this. So we're given this equation to start with. And then they're giving us a bunch of answers here. This is one of those weird situations where we're looking at the answer as a part of the question because it wants to know which of the following values is the greatest. So which one of these values down below here would be the largest? And again, you say, well, what am I supposed to do? I got a picture of a graph, but the graph up above is the function f. The graph up above isn't the function g that they're asking me for in these equations. G is the equation that they actually gave us right here. So what we're being asked to find right now, for A, we're looking at g of negative 3. For B, it's g of negative 2. For C, we're looking at g of 1. D is g of 0, and then E is g of 2. This is just function notation, right? Again, this is why you got to stop and not freak out. This is just saying take the g equation and wherever you see an x in it, plug in negative 3. So if we take our equation and we plug it in and see what's going on, it's asking us to find the antiderivative from negative 2, and then I plug in negative 3 for x of f of t dt. Well, that is something I know how to do because integrals are just the area between the curve and the x-axis, right? And when we're doing a problem like this, the important thing to keep in mind is that any area that we see up above the x-axis, this is all positive area. And anything we see area down below the x-axis, this is negative area. And what they're probably asking you to do is just add up some areas and see what's happening there. So again, the function notation with an integral, and it freaks you out at first, but just remind yourself, function notation always works the same. Whatever they replace x with, I replace x with. So here we're being asked to find the antiderivative from negative 2 to negative 3 on the first one. Well, first thing you got to remind yourself on one of these is that the smaller number always needs to be on bottom and the larger number always needs to stay on top. So in order to flip those bounds, you do what I just call pulling a negative. You pull a negative to the front and that flips the bounds. And now if I look back there, really, I just got to say, okay, well, what's going on here? What's positive, what's negative? So I'm going from negative 2 back to negative 3. And really you just sort of count boxes because you don't really care what the units are. You just want to know how many of them there are. So this would be 1, 2, and maybe call that a half right there. So the integral piece of this would have equaled 2.5, but that negative on the front changes that to a negative 2.5. Probably not our answer because negatives usually don't win out in these situations. So in the next one, we're now plugging in negative 2. So I take the antiderivative of negative 2 and then plugging in negative 2 on top. Well, here what they want you to quickly identify is that negative 2 to the negative 2, anytime the bounds are the same, the answer to all of those problems is always 0. Then we're going to go to the third option here. So we're looking from negative 2, and this time our x is 1, to f of t dt. So starting here at negative 2 and going all the way down here to 1, we'd see that we have nothing but a bunch of positive areas. So as I count that up, this would be 1, 2. This would be like, you can kind of see that this piece here would sort of fill in on that piece right there. So you could call that 3 between those two. And then we're looking at a half right there. So I would estimate that at about 3.5. And that's all you're trying to do is just get a sense of what it is. You don't need to know the full actual number necessarily. Especially on something like this, you just want to be quick about it. So the next one's plugging 0 in for x. So now we're looking at the integral from negative 2 to 0 of this thing. So starting here again at negative 2, this time ending right here at 0. And what you should see real quick is it looks like the last answer, except it's missing this 1/2 portion right there. So that would actually just be our 1, 2, 3 that we saw on the other one. And then the last one here, we end up going from negative 2 to 2 of f of t dt. So let's see, starting at -2 all the way down here and going to +2. So we would get everything we got from 0 to 1. So we would get all of this space right here. But then this time I've got a -1/2. That's actually the wrong place to label it. If you were going to label it, you'd probably put it there because it's the area between the curve and the x-axis. So that -1/2 would actually cancel out with this +1/2 over here. And again, that would leave us with 1, 2, 3 spaces left. And so looking at these now, we can see that the largest value would have been C because it had the most amount of positive area. So our answer would have been G of 1. So remind yourself, just because there's an integral in your equation doesn't mean it's a bad thing. Function notation always works the same. Just take that x and plug it in everywhere you see an x in your formula. Thanks for watching my video. If you liked it, please click that like button and subscribe. And also share it with your friends and anyone else you know who might be crying about an upcoming AP Calc test. You can find more videos from me, more sample AP Calc questions, and my complete AP Calc study guide over at my website, apcalcprep.com. Have a great one.